So as we continue working with exponential functions, one of our special exponential functions is going to be the base e. The base e. And it is a constant, and if we were to put it into the calculator, we would see something along this lines represented. It is often referred to as Euler's number for the gentleman who started using it in 1720 something to represent a constant value. As we look at it, sometimes you'll hear it called Euler's number, sometimes it's just E, but it is a irrational number that if you plug E into the calculator, it will give you this value. So as we utilize it, just understand that it's a holder, much like pi. Pi has a value, a numerical value, but we use pi as an abbreviate. So using it, things that we'll see it in is continuous compounding interest. So that formula calls for E, and then of course this formula is on our state reference sheet to be able to use it. But we would use this as any other base for an exponent. So my exponent rules still apply. When I have like bases being multiplied together, that means I add the exponents. Same thing that we would have done before. When I have a base raised to an exponent, so we would do the same thing, that we would multiply. We would multiply our exponents, and then when we have division, e, e to the 7th divided by e to the 5th would be e to the 7 minus 5. So just thinking about the same rules apply that we've used in previous steps for our exponents. So this is just another number that we use as a base. Okay, so here, again, being able to utilize our exponent rules, and I'll give you a second to do this check, and then, stop the video and see if you can get it correct, and then come back and check your answer. So let's see. Looking at this, we know that we have all base e, and we have e to the 4th times e to the 3rd times e to the 1st. So that should be e to the 4 plus 3 plus 1, which is e to the 8th. In this next example, we have this exponent goes to both the coefficient and the variable, or in this case, e. So we should have e to the 1 times 4 times, sorry, I said e, 6 to the 1 times 4, because that is 6 to the 1st. And then we have e to the 2nd times 4, so we have, let's see here, 6 to the 4th, e to the 8th, which is going to equal 36 times 36. 36 times 36, or e to the 4th, is going to be 1,290. I said e again. 6 to the 4th, 1,296 e to the 8th. And let's see here. If I go ahead and simplify, I know that 60 divided by 12 is going to be 5, and then we would have e to the 6th minus 2, which is going to be 5 e to the 4th. So simplifying those using the exponent rules that we have already worked with. Now, when it comes to graphing these functions, we're not necessarily going to spend a lot of time graphing these functions, but what we can understand is those same transformations that we've been studying with all of our functions also apply here. So looking at this formula, think about a parent formula. So the parent function probably looks something like a e to the x minus h plus k. So thinking about those transformations, we know that from the past, the a value stretches it, compresses it, or makes it flip over the x-axis. We know that the x value moves it left or right on the number line, and then we know that the outside k value makes it move up or down, or that's like my y-intercept. So with that, right here, we can, or has been used as our y-intercept. So we can use this to understand how is this being transformed, and being able to see that This minus 2, it is not only being reflected, but it is being stretched. H of 3, that means we're moving right along the x-axis because that's our positive direction. K of 2 means we're moving up, that's our positive direction. The domain and range, just to look at these two functions, this blue function right here is the parent function, the orange function is the transformation. Okay, so the domain of my parent function is going to be all real numbers, just like other exponential equations that we've worked with. And then the domain of my transformation also appears to be all real numbers because it goes forever and ever to the negative, goes forever and ever to the positive x, negative x. And then the range of that parent function, of course, we have an asymptote that occurs at 0. So the range for the parent function is going to be for all values such that y is greater than 0. And in this case, since we translated it up 2 and it goes downward, its range is going to be for all real numbers less than 2, because 2 is going to be its asymptote, that thing that it approaches but never touches. Okay. Now, so that's just being able to understand those transformations. And again, here, you should be able to understand what is the rate of change. That is, in essence, your slope, your rise over your run, going from the x value of -4 to the x value of 1. So thinking about what is that, when x is -1 right here, and then when x is -4 right here, what is the basic rate of change between those 2 points, or slope? So you have an input and an output. So if you look at the calculator and you were to put this function into the graphing calculator right here, when I put in x of -4, what is my output? When I put in -1, what is my output? And it turns out that it is going to be 1.998 and then 1.963. That's what the calculator is going to show you. Or if we were to simply plug in the value of x is -4, so that would be here, that would be -2e raised to the -4 minus 3 plus 2. Okay, and then whatever that number is, that's my output. This is my output value. So now when you do your determine the average rate of change, we want to take our y2 minus our y1 over our x2 minus our x1. Okay, so there you go. That's what we have here. We came up with a value of -0.012, which is a very, very flat line, but not completely horizontal. And then we can see that, and again, looking at that, that's fairly horizontal. And as we continue to do that, if I go from when x is 0 to x is 3, that, we can see a little bit more slope there. So when they plug in those values, of course, they came up with your x and y values, and they turn around and came up with a -0.633. Okay, and that seems about right. That definitely, if I were to just try to count that, I could say, well, I went down 1, 2, over 1, 2, 3, so that's 2/3. 2/3 would be 0.67 repeating, so absolutely very close. It's what it's not precise, but we would have been close. And then from 4 to 8, if we can go here, when x is 4 to when x is 8, it's probably going to be down here somewhere. What is that slope going to be? Okay, and it's obviously not going to be that far, but there you go. What is that slope going to be? And that's what they did. They put the x and the y, plugged it into their slope formula, and came up with the missing slopes. That is determining your average rate of change over a given interval. And the interval is going to be, these are my x values, x1, x2. And then you have to plug that in to get the corresponding y values to calculate the average rate of change. So here, if we were to graph this, what is my domain and range? Let's see. That is not an absolutely beautiful function, but that's about the general shape. We have an asymptote of 2, and then it starts to go and then starts to fall, and we have that general shape of that function. And what is the domain? Well, the domain we've determined is all real numbers. I'm just going to say all real numbers, and then my range is going to go from, again, just because it's a different type of function doesn't mean that we can't identify these basic characteristics. The greatest y value appears to be 2, but we never touch 2. It's that asymptote. We're never going to get to 2. So it's your range is going to be for all values of y such that y is less than 2. Okay, it should look something like that. Now, when you plug in this function and you look at your tables, I'm going to just, when I look at my tables, I have what? -6, -3, -1, 1, and 4. And what are my tables going to be? So there you go. When I plug that graph or that function into the graphing calculator, go into y equals, and I come up, I have some ordered pairs now that we can see. -6 is 1.9933. -3 is going to be 1.8647. So there's my ordered pairs there. Then I have -1 is 1, and then 1 is going to be -5.389. So these are my ordered pairs that I'm going to use. So you can use the slope formula or the rate of change formula to calculate that. So please give it an attempt and then check your answers. Okay, so when you go ahead and you plug those values in using the slope formula, let's see what I have. Got to remember that a negative times a negative is a positive. So the first one ends up at -0.042866 repeating. Round that one up to -0.043. Okay, this rounds up to a 3. Now when I do the next set, I end up with 1 minus a -5.389 divided by -1 minus 1, or divided by -2. So I end up with a -3.1945, or I rounded that up to 3.195 negative. Now the next one, depending on where because of the decimal, it's an extremely small decimal here that we're talking about, but depending on where you round your decimal, if you use these numbers and you rounded to the third or fourth decimal, depending on whatever, when you plugged in these values, your answer, when I took my y2 minus my y1 over my x2 minus my x1, I came up with this, and equals -47.004. That is using these decimals where they've been rounded according to this table. If you were to carry it out, not rounding until the very last step, so letting the calculator carry the number forward by using your answer key, you would have ended up with -47.008. So depending on where you're rounding, you could ultimately have a little bit different answer, but in reality, it's so close. Just understanding that it's probably a rounding difference. So those are two possible answers that we could have come up with there. So moving on to applying that, well, when we use continuous compounding interest, that's the formula we're going to use, that the amount is going to be equal to the principal times e raised to the rate times time. Okay, those letters should mean something to you already at this point in time. So LaShandra deposited $1,500, $1,500 in a savings account that pays 2.5% annual interest compounding continuously. Again, compounding continuous formula is labeled on your reference sheet. After 4 years, what will the balance of LaShandra's account be? What will be the balance of Chandra's account? So what is my rate? What is my time? And it tells me here that the amount is going to be equal to the principal that I put in. My initial investment was $1,500 times Euler's number E, and then the exponent is going to be the rate times time. They said time was 4 years, and the rate, remember, when you're converting a rate, you have to move your decimal place 2 points. So 2.5 is actually going to be 0.25. Okay, and then when you plug this into the graphing calculator or any calculator, it's going to come up with a number of 1,657.76. And there you go. LaShandra will have this much money in her savings account. And definitely want to go to the second decimal place because that would be your pennies, right? You want to count your pennies. So that would have, that's knowing the applicability of your values. Yeah, you definitely, when talking about money, you go to the hundredths place. And then, so in this example, look at this check, remembering that the, let me see here, continuously, right? Continuously. So we're looking at that. The amount is going to be equal to the principal times Euler's number times the rate times the time, and being able to calculate. So stop the graph. Oh, goodness. Stop the video and then give it a shot and then go back and check your answers. Okay, so my principal should be 4,000. Oops, sort of looks like I put it in the wrong place. The amount is going to be equal to my principal, 4,500 times E, and the rate, I took 12.5% and converted it to a decimal, so that is going to be 0.125 times T. And then that would be my function that will allow me to find out the value, and then evaluate that function. After 5 years, if it continues to grow in this way, Alejandro's investment will be worth what, and then after 12 years it will be worth what. Now the easiest thing to do here is to put this into your graphing calculator. Again, y1, and then input this into my y1 category. So when you put it into your calculator, you can do it out manually, or you can put it into y equals. I do y equals because I'm looking for more than one value. So when I plug this in, let me see here, x being my variable, so at 5 years, my value is going to be worth $8,407.1. Now, it looks like my decimals may be off, so I may want to make sure that I do have the right answers. Let's see, what would the decimal place? I can change that in the calculator so I can show the proper number of decimal places. And when I do that, it looks like this is actually going to be 11.11 when you change your decimal places. So the answer is going to be that continuous investment would be $8,407.11. At 12 years, again, I need to change the decimal place. It looks like it's going to be 20,000, and it has rounded up. So when you go to check your decimal places, it's actually going to be $20,167.60 dollars. Okay, so because of the way the calculator was set up, it's only showing me certain values. So you definitely want to make sure that we are getting to the hundredth place, so we don't round up and cheat ourselves or take too much money. So there you go. That's doing that check. And then here, using technology again, there's different ways to be able to calculate this, but what they're saying is if solving using a system again, and we've done this both ways, you can take one side of your equation and plug it into y1. You can take the other side of your equation and plug it into y2, and then calculate their intersection point, and it will give you this point right there. Now, when you do that, when you use your graphing calculator and calculate it, it will be 0.916. That is my x value there. Is going to be 0.916. So that would be my solution. You can also use a table. So here they had to, let me see here. It says you can use a table feature to verify the solution. So when I plug in the table, you can, again, we've talked about using the plus sign and adjusting down to the 0.001, so we can go to the thousandths, so we can look at different decimal places. And then when you plug those, when you check your table and go to that certain point, turns out we find out that if you use 0.915 as a starting value, and then you go by your thousandths, so you would set it to 0.01. Again, that would be the interval that it's going to start going in, and then you start to see what is going on there, and you can see your values. You can verify it. Another way would have been to take this, and in y1, remember creating that related function. I would have what? 5 is equal to 2e to the x power. Well, if I subtract 5 from both sides, you end up with 0 is equal to 2e to the x power minus 5. If you plug that in there into the graphing calculator, 2ex minus 5, you're just looking for your zeros. You want to calculate, and then you want to calculate your 0, and wherever it crosses over the x-axis would also give you the solution of 0.916. So there's different ways that that calculator will come up with the work for you, and we've done that in previous sections, so just so you know. And then here, I will tell you that if you go ahead and try to do this either way that you like, pause it, check your answer. But when you come back, I hope that you ended up with 4.39 as my intersection point. So again, two ways to do that. Y1 is equal to negative 6. Y2 is equal to negative 1.5 e to the x minus 3. And then looking here, we want to find their intersection point. Intersection. Here, or you could say that y1 is equal to negative 1.5 e to the x minus 3 plus 6. That's that related function because I add 6 to both sides. And looking for your zeros, whichever one happens to work for you. Okay, so different ways to use technology to find those values. So without further ado, let's go ahead and do a little bit of practice in class. And this is repetitious, and we're getting used to these acts.